So I will begin with abstract theorems for dynamic entropy. But each time I will apply, for application, I will consider the model we considered yesterday. So in this way, you will recall all the notations from yesterday, and so after half an hour, you will feel better and you feel good, so then our friendship is no longer important, okay? So let me begin with the notion of dynamic or entropy. So we will consider the general case. X is a compact matrix space. And you have a transformation, which is a continuous transformation. Of X, okay? Then you know that ball and ball, we are defined as follows. For any x equals to x, and epsilon bigger than 0, n to n, then you have this notation, Ex epsilon n is the collection of points, so that the iteration of this y under t will stay within the orbit this x up to time n. Okay, so this is y belongs to this one, and you have the tj y and tjx is always less or equal. No, not equal. I put less equals to. This is n minus 1. Or n, it's the same. Okay? N minus 1. Okay. So the entropy, the classical entropy of the invariant measure is defined as follows. We just use this classical definition. This as n goes to infinity. Okay, this is the entropy. So this measures, so the decay rate of this ball and ball of this measure actually measures how the points are separated in this iteration of the map T. Okay, so this HM is this average rate of how the points are separated through this iteration. This is entropy. So for entropy, we have the fundamental inequality, which is called Rudel. Spell correct? Rudel inequality. Okay, so this is the theorem, which is very fundamental. So you only need few assumptions. We assume this x is a compact manifold. And this T, the transformation is C1. Okay, C1 mapping of X. Then the conclusion is for any T invariant measure M, you will have this measure, theoretical entropy of this M is less or equal to the supreme of K of the average growth rate of the K wedge products, okay? So let me write down this first because this notation is wrong. This is a tangent map, okay? So this is a wedge product, So how to understand this? You can consider this T in the linear case. So you will have different directions, expanding, contraction, and no change, right? And then what are these bowing balls? Actually, these measures, how it shrinks actually is related to this expanding ratio. How you expand, how the map will expand. So what is on the right side? This is the maximum possibility that the volume are expanding. When we consider this cave wedge product, that means you consider the possible volume expanding if you restrict to kth dimensional subspaces, right? So this is already the maximum possible of expanding. That's why this entropy is always less or equal to this one, okay? So this is real inequality. And let's look at this inequality in our setting yesterday. So, yep, but I prefer to put limit sub there. Yeah, you have the Icelandic theorem, I think, yes. Okay.
Some properties that characterize the quality.
Which one?
I mean, the entropy is always less than the span over K, blah, blah, blah.
Yeah.
I'm wondering if there are some properties that characterize the equality.
Yeah, of course. That's, yeah. That's one topic in dynamic system. Okay. So, sense theory and things. You are correct. Good. And so what's the example is, we go back to yesterday. Okay. So we consider this x equals to Sm. So this is the limit I can go, right, for Blackboard? Okay, this is my limit. All right. So we consider x equals to this one, and then again we consider this mg is compact. Boundaryless. And actually C2 should be fine So, but yesterday's setting is infinity. So smooth. Remaining manifold. With negative curvature.
You show that the definition of entropy
That's one way to present it.
That's why the integral.
Yeah.
You integrate.
Oh, you mean epsilon super E should be outside. Yeah. Yeah. Okay. Anyway, in our case, it doesn't matter, right? Yeah. Yeah. To be safe. This is okay. So in this case, so if we have M, which is geodesic flow invariant, measure. So most cases we consider probability. Then what we have is actually application of this Roller inequality is this entropy is always less or equal to T, because T can be negative, means the flow in the other direction, right? So then here is what is the thing here? Is the thing which appeared yesterday is the B. Okay, this is a different B. That is Bowen-Bow, and here is the real B we considered yesterday. So DM. Okay, this is. So let me recall at this moment what is this Laplacian of Postman function thing, and it's always helpful to think this basic example. So for the pancreatic case, so you consider the geodesic flow, then actually what is your tangent space? TSM, it's of three-dimensional. It's three-dimensional, right? And in this constant curvature case, actually you can see that you have one direction which is contraction, you have the contracting direction. And this contracting direction is associated with this. So you draw the picture, you have V, it goes to T. This, for this point, the stable or the strong stable manifold actually are the collections of these vectors, which will point as this C, right? This is okay. So what is the action? Then the flow, geodesic flow, is just moving along the geodesics. So you have the contraction. You have the contraction. This is one dimensional, and the flow direction is just parallelly moving along the geodesic. So it will not change anything. And you have another direction corresponds to the expanding direction. Okay. So what is the possible expanding rate of this geodesic flow? It's actually the contraction of volumes in the strong stable directions along this flow, right? So if you looking this way, then what is the B here? Yesterday I put it here, Bxc. This is the Laplacian along the weak stable foliation of this Postman function, and which is minus divergence S of the geodesic spray, and also this one will give you the geometric interpretation of this B as the mean curvature of this Horus field. But if you are not familiar with this geometry thing, the one way you can think is what I said. This B actually tells you the contraction ratio of volumes when you restrict yourself to the contraction, these directions, then you let this flow to, you travel along this flow to see what's the contraction ratio. So this is the B. That's what I put there in last lecture. This is the logarithm, the derivative of the logarithm of the determinant of the tangent map along the strong stable foliation. Right? This is the example. Okay? So then you see this guy should be S or equals to T times this quantity. This is one example, and I want to put another theorem, which says which will tell you another abundance. Okay, so this. I think it's 70. And so for SM, this is our phi t, and M as above. So what you will have, actually, for any T-invariant probability measure, you consider its measure theoretical entropy. It's also less or equal to T times V. V is the volume entropy. So this V, as we defined yesterday, is the growth, exponential growth rate of volume of Bx. This is in the universal cover. Okay, this is the volume entropy. So what is this? Actually, because in the negative curvature, this V will equals to the topological entropy of this flow. So this inequality is just says the measure theoretical entropy should be bounded by the maximum one, because topological entropy is the maximum among all the invariant measures, probability measures of this guy. Right. Thank you. Right. So this many. Okay. So now you have two upbounds. So it's natural to ask what's the relationship between these two bounds and are they related? Because this is the volume, expanding volume rate, and this is the one once we restrict ourselves to the contraction directions. Okay? So we will study this using the thermodynamical formalism. So I move to the second part. thermodynamic formalism. So we let this xt as above. That means the general case is okay. Xt. And then you define a measure, you define pressure P of F of a continuous function. F as what? So I just put a lazy definition here because it's a variational principle. This PF, I just defined as, okay, you have to prove this. You have to give the definition and then prove this. So okay. So, okay, I will choose the lazy one to have this as a definition. So you take the supremum of all the invariant probabilities. M is T invariant probability measure, and what is the measure theoretical entropy of this M, then plus the integral of F with respect to M. So what is this pressure? Intuitively, it's a kind of measurement of the complexity of the system using a reference measure, a reference function F, using an observation function. So this entropy is also a kind of a complexity of the system. So you see that the topological entropy will correspond to the case this F equals to 0. Okay, so this is the pressure function. So then what we want to say are several facts, just facts. So the first thing, as we said, is now we consider this x equals to Sm, and also phi 1. You can take this t as the time 1 map of geodesic flow, okay? Then the first fact is biroreal and Manning's by their inequalities, actually you already see immediately is P minus B. B is the Laplacian of Postman function. This guy is always less or equal to 0, and also P zero is, let me see, P0 is less or equal to V, right? Okay, so that's it. Okay, so how about the second fact? The second fact is, I want to say, actually you have equality here. Actually you have this one equals to this. Okay, why? It's because you have equilibrium states in this case. I mean, the supremum can be a 10. What is the candidate for this one? Minus, actually is the Rouel measure, which is nothing, just the volume. We have to show the volume is invariant on the geodesic flow, and also we need to show this entropy phi 1 will equal to the integral of this b with respect to this one, right? But you almost see this, because what can be the entropy for volume? This is just the b, the integral of b with respect to volume is just the maximum possibility of this expanding ratio or the contraction ratio. So this makes sense. And about this part, actually you will have the maximal entropy measure, which also has the name as Bowen-Margulis, I think. Measure, which is actually the maximum entropy measure, because in this case, I will show later, I have to construct this measure first and then convince you that its entropy is equals to. But in the negative curvature case, this is just the topological entropy of this system. So this is the Bowen-Margulis measure. So this actually, they are not facts. We will have to explain in this. This is the second one. And what is the one? So the third one, I want to promote it to be the theorem. So we have Sm and phi 1 or phi t as above. And then you will have this inequalities. You take the infimum among all the t invariants probability measure of the integral of this guy, of b. I claim is less or equal to the entropy of this Liouville measure, which I will use capital H. This is always less or equals to capital H, and this is always less equal to V, and this is okay. So you will have this, and with any one of the equalities hold if and only if this Liouville measure will coincide with the maximal entropy measure, Bm. Okay? So this is a statement, and moreover, in that case, we actually have the integral of this b with respect to any measure will equal to the volume entropy. So, okay? And here, this m is phi invariant probability measure. Okay? So this is our theorem, and what's the proof? So you see the inequalities are just consequences of the Rouleau and Monet's inequalities. right? This part. Well, Postman. Okay. So you see that? Let's see. So first V is the topological entropy. It's attained at Bowen-Margulis measure, and then this guy, this measure theoretical one, should be less or equal to the integral with respect to Bn. So of course it's less or equals to supremum. And H less equals to V is because V is the topological entropy. So this is true. And how about this part? Because H, you have the Liouville measure, so the entropy, this H is just the integral of this one, so of course it's less or equal to the infill. So this is the inequality part. And so how about the rest part? Rest part. Okay, so the rest part is by convex analysis thing, and then plus dynamics. Okay, looks to be fancy, but actually, you see, it's very short. So what's that? And now we are back to see what's the use of pressure function in this case. I said it's a complexity when you try to measure the complexity from the observation functions, okay? So what we know, the fact, the other facts. So let's continue. First thing you see, this P is convex among the invariant measures because it's a supremum of a fine function. So it's convex. So this is the first point. And then the second thing is now if you consider one parameter of Holder continuous function, it will hurt in more general case, but I just want to consider our case. So we will say this S to Fs is a C2 curve, a C1 curve of Holder continuous functions. Okay, so each one is Holder continuous, and so actually in this case, then see this S goes to P Fs. Okay, this one actually in our case is analytic. So if you so in general you see if you know this S goes to the pressure of Fs is C1 at S0, then, and you know other things, and you know this M naught is invariant probability measure, so that PFS naught will equal to this one. So it's an equivalent state if this N naught is the equivalent state for Fs naught plus Fs naught dm. Okay, so the conclusion is that you see S equals to S0. This is curve. Yeah. Some point. Okay, so then you see the differential of this pressure function of SS, fs at s equals to s naught. Actually, see that this guy is just the differential of this fs, evaluate it at s equals to s naught, then take the integral with respect to this one. Yeah. Yeah. So here I assume this fs to be Herder. Yeah, for this one. In S. In S. It's, yeah, you are right. Thank you. Yeah. No, our curve is S to the value, to the pressure of Fs. So later, no, this is S goes to the pressure. Yeah. It's a C1 curve of Herder continuous function. So maybe let me, in our case, actually, what we will consider here is Fs y equals to Sb. C1 curve in the space of Herder continuous functions. When I say it's convex or okay, we want this line. It's convex. I mean here. I mean, you mean here? I say so. No. This is S goes to the pressure.
It is F1 plus F, and F1 plus 1 minus Tf, the affine line going over the 51.
Yes, it is that. If you can have a function of R2 that is complex, and then a curve of R2 convex line.
You mean this line?
This Fs
Probability C1 curve has to be an affine line. That's what the Chauffeur says.
So, okay, so what should I do?
Just write line.
The line.
A line, you mean, here?
Yes.
We want a line, okay? Yeah. I need to, you mean we need to...
If your curve is this way,
yeah. Oh, I see. I finally understand your question in the space of Herder continuous function. Here is P is convex. Okay. So
this doesn't need to be a line, right? I mean,
we consider this case. Much better? Much better?
this convex, that's why you want to see that it's not S plus convex.
that means it's along lines it's convex.
Along lines.
But because we have been variating at a this is an arbitrary variation.
This is our fs. One parameter.
What is the conclusion? You want to say that P of fs is convex? Sorry, I just mistake somewhere. You say that P of fs is convex? You only said C1, sorry. Maybe, okay, sorry.
It's already past half an hour, so. So it doesn't matter now. Okay. So what should I do? I do what I want to do, and so okay. I can leave it as for discussion, not for access. Discussion. So you consider this SB, the pressure of SB. B is a Hölder continuous function that we defined before. So then you have this pressure. You take the derivative of this guy in S, and then you see potential is just the integral of this one. Okay? So it's in our case we don't have problem because B is Hölder, you have unique equilibrium state. Then you use the definition, actually you can see that the differential is this guy. So now you are back to the theorem we want to prove. So once you start from this, then you see the slope of this function. S goes to P SB at S equal to -1 is just H, right? Okay, so this first point. And then the slope of this one at S equals to 0 is just the topological entropy, the V is V. Okay? So we are in B is a Hölder continuous function on Sm, and in this setting actually you can show that this S goes to P SB is real analytic. So you see why the rest conclusions are correct. So once you have the equalities of any one of them, this is what? This is this P is convex, and this is the tangency as this S goes to -infinity. And this one is the tangency or the slope of the curve as this S goes to infinity. So once you have any one of these inequalities, actually then we'll force this one to be equal. These two should be equal. Because this curve is analytic. This is slope at -1 and this is slope at S equals to 0. It's real analytic. If you already have constants in the middle part and it's analytic, you have to be the straight line. So you have to be constant. Okay. So this is the first part. And now we move to the second part. because of this Leuven measure and the Bowen-Margulis measure, we'll always enter this kind of entropy formula. We want to understand these measures. So we want to visualize these two measures in the universal cover space. And I will begin with Leuven measure. Leuven measure. So Leuven measure So the Leuven measure is just a volume. And if you go upstairs, SM tutor, since we already identified this guy with M tutor times the boundary. So, okay? So it's a volume. So here you have the unit tangent bundle at x. So you will have a Lebesgue measure. Okay. So you have tau x. We will let this tau x to denote the Lebesgue measure. Probability measure. Then many times we will push this to the boundary, geometric boundary. So you will obtain the measure on the boundary is always denoted by lambda x. Is you measure this, take it back to this SM tutor. So lambda x is the pullback of the projection from here to the boundary, okay? So this is the pullback of this one, tau x. Okay? So you see what's the lift of this Leuven measure to SM tutor. Actually, many times we will use this notation as, so I erased what I wrote yesterday here, and still, maybe I put here, so I don't want. Tutor. Yeah, visual measure at x, okay? So this M tutor will satisfies. So this means dml wedge where equals to m wedge, the boundary wedge, and f x c d lambda x. The volume x, and because downstairs we normalize it, so we divide it by the volume of m. Okay? So, erase this part. So maybe I just put it here. So what is the fact about this dual measure? We recall it again, is that the first thing is in this coordinate, if we give this measure in this way, we have to show this guy is invariant, and under the geodesic flow. Under the geodesic flow. So why this is true, almost leave it as an exercise. Is using the Jacobian field theory yesterday, is that because now you have T, you consider the volume form in TSM. Okay, so upstairs is TSM. Tutor? So this is 2D minus 1 dimension, right? Because M is a D dimension, 2D minus 1 dimension, okay? So actually, for the geodesic flow in the negative curvature case, then you will have the flow direction, that's one direction, let's say it. It's a 2D minus 1, then you have one direction corresponding to the flow. And you have D minus 1 direction corresponding to the contraction. And D minus 1 direction corresponding to expanding direction. Okay, you just apply this to the basic example. You will see this one. Okay, so actually you see if for the tangent in this, for vector in this space, yesterday we said we can use the Jacobian field. Okay, so the tangent vector at the initial is this one. So the flow action, the flow will take this one, goes to JT and J prime T. Okay, then it's standard to consider the Wronski symplectic form. Wronski symplectic form on this. You have two, J1 prime, and J2 prime. You define this one as just like the determinant. So this is J1, J2, this one, then plus minus this J1 prime and J2. Okay? So using the Jacobian equation I gave you yesterday, actually you can show this guy is invariant under T. So using this, actually we can pair the vector. So you want to have the volume form, right? Volume form. Actually, you can pair the vectors in the expanding direction and the contraction direction, so that this guy is constant. So what does that mean? You want to have the 2D minus 1 volume. So one direction is the flow direction, no change, already know. And the other two directions, actually you can pair them with, you have the contraction ratio. Here is, say, minus lambda. Actually you will pair it with the one with expanding ratio lambda. So you pair them using this Wronski. So actually, what does it mean? The volume form, what I want to say is that this D minus 1 wedge product of this Wronski form, and then wedge dt is just the volume form. And because you use the Jacobian, this guy is invariant under T, so actually the volume form is preserved under the geodesic flow. So the big measure is preserved. It's a T invariant measure. It's Okay, that's important. And I can state this theorem once again, is that for the Wave measure, actually this measure theoretical entropy equals to the integral of this B with respect to this measure, okay? And you also can lift this to upstairs, but then you have to restrict yourself to the fundamental domain of this M times the boundary of this B, dML, okay? So this is the Wave measure. Okay. And how about the maximum entropy measure? The first part, so is some relevant construction at the boundary. Actually, Peter already mentioned in the morning is Patterson-Sullivan measure. So the only difference is in our case, in the manifold case, we will have the class of conformal class of measures on the boundary. So afternoon is a tutorial time, usual. So let me begin with the tutorials here. So let me remind you of the Postman function. Okay. So the Postman function of this guy is defined as this z goes to c. Here your z, the difference of the distance of minus dx. Okay, this is the Postman function. So what's the advantage of this one? Okay, so one thing is that you see as this z goes along the geodesic in this direction toward this c. Say if this y is here, is gamma x c, this geodesic at time t. So the Postman function, the value at this y is just minus t, right? So this is the first observation. Gamma x c, t is just minus t. So gradient of Postman function is the reverse direction of the geodesic spray, right? This is one thing. And the other thing is this Postman function has this cocycle property. So let me put it here, is that if you have xc and you evaluate, because I'm short of notations, I cannot use g. I already used g for metric, so I put beta here with different meaning. So this is equals to b. Beta is any element of the fundamental group. Okay. So actually this one, you can see this will equals to the bx beta inverse c y then plus bx c beta x, right? So this, with this cocycle property, let me see how many pages are left. Okay, I leave it as an exercise. Exercise, you have this cocycle property. Because you can change them all the time, the same time, and then you need to change the base point. This part corresponds to the change of base point you will have. Okay, you have to do this once to understand Postman function. Okay. Okay. So what we learned from morning, I would say it's a proposition, is that you can construct a class of measures on the boundary, which is, in some sense, is the Hausdorff measure on the boundary. If you endure this boundary with the Gromov distance, that means for any 2 points, the visual meaning is e to the power of distance almost. But you need to use a Gromov product, something, okay? So then, in this case, actually, this class of Poisson-Sullivan measure is just the Hausdorff measure on the boundary. So what does that mean? So the conclusion is there exists a family of measures on the geometric boundary, which is the class. I will use the notation of nu x. Such that, so if you have element act on this one, it will equals to okay, first thing. And the second thing is that the Radon-Nikodym derivative equals to minus v, vx, cy. Okay, so you will see if you want to construct this nu x as a kind of Hausdorff measure at the boundary, actually the Postman function will appear naturally. So this family, and the conclusion is this family is unique if we normalize it, if we assume this guy equals to 1. Okay, and so moreover, the measures are continuous, means the measures has no atoms. Okay. So what's that? We can give a short proof to recall what we learned in the morning. So you have this observation. First, for this class of measure, you only need to construct for a fixed x and all the beta x. So this is the first thing. You have this observation. We fix this x naught belongs to M tutor. Okay? And assume that we can construct x naught such that actually you have these two properties here. First thing is this mu x naught. The second thing is the Radon-Nikodym derivative. E to the V. That's what we said. So, okay, suppose you already construct this class of measure just for a fixed x naught and also the value at beta act on this x naught, the orbit, along the orbit. Okay, then we can define for other points, for y belongs to n theta, we just take this as a definition. So we define y such that the Radon-Nikodym derivative of this one with respect to this guy is e to the power minus v bx naught cos c. This b is the Postman function. Okay, we just take this as a definition. So once we obtain this class for along the orbit of x naught, then for other y, we just take this as a definition. So then what left, we only need to show that two things. With this definition, actually this new y, for arbitrary y, you will always have the first property. Okay? So we have two things. The first thing is with this definition, actually, you can see that what we want to show is this nu at beta y will equal to this beta act on mu. We have to verify this because we just define it using x naught. Okay, so if you use this, if you use this, and you will see that actually you play with these two definitions here, then you can see that, let me put it in this way, this the action of this one, the Radon-Nikodym derivative of this at C, where equals to what? Actually is, you put beta at nu x naught here, right? Here, and then you will have, let me put it in this way. So you use that definition, you will see you will get e to the power minus b x naught. Here you have, this one will be beta minus here, so beta minus c y, and then times e to the power minus b and times bx naught c beta x naught. Okay, so we haven't erased the cocycle property there, so you have to check that. So this part, actually, you will equals to what? That's what it says there, e to the power minus b, bx naught, c beta y. That's exactly the definition from this new beta. So, okay, this is the observation that we only need to construct this class of Hausdorff-like measure for a fixed x naught and also for Ross points along this action of x naught. Okay, act on. So then, what we know is completely similar to the case. So next step. So the construction of this new beta x naught. So if you have that in your mind, that to construct this kind of Hausdorff dimension thing at the boundary, then you will see the following construction is very natural. So for S greater than V, we take now we first consider measures not going to the boundary, just M-tutor. So you consider the Radon-Nikodym derivative with respect to this y is on the universal curve, and this guy with respect to what? To the volume is defined in this way. E to the power minus s d beta x naught. So because I want beta x naught here, y, and the integral to volume, and e to the power minus s d beta x naught y and d volume. Where's y? Okay, sorry. Maybe should, okay. We use z, okay, it's better, because otherwise you will get confused. Thanks. So what does that mean? I mean, it's a kind of, you consider here's y, you consider here's your x. It's kind of vertical, if you say this way. It's a kind of this part can be considered as just the ratio to the power, some power, right? Okay. So this part is just to normalize this, and since we want to construct Hausdorff dimension thing, Hausdorff measure thing, so you will see this V is the critical value, right? For S bigger than that, and then you will have convergence, and less than that, you will have divergence of this one. But at S equals to V, it's not sure. So you don't know. Okay? So you see, the first case, to finish this, I finish this here. Put it here. I finish this with, okay? So if we assume the integral of this guy is where it goes to infinity, e to the power minus s, the x naught, actually it doesn't matter, the x naught and the z right? D, okay. And the volume, this one, where it goes to infinity as goes to V, decrease to V. Then you can choose we can choose this SM. You can choose some subsequence so that this defined in this way. So here I can put beta, it doesn't matter. Okay, so you can choose this one so that what we want to construct this. Okay, so simpler is you consider x naught first, right, with this definition, and then you assume this diverges, then you can see that the measure goes to boundary actually where it has no atom, right? This is one observation. And then once we assume this goes to infinity, then we can choose SM such that the subsequence will converge. So x naught SM in the weak star sense will converges to x. Okay? So then we set, for other gamma, we set beta x naught, what? Also the same sequence. You have to show it will convergence. So you see, yes, it will converge. Why is because for each S, you measure the difference. Yeah, okay. Beta, okay, this is defined for. Oh yeah, it's defined in this way. For each S, we're right. Okay. So you set this one, then you can see the Postman function will appear naturally because the differential of beta x naught, the Radon-Nikodym derivative by our definition at y will equals to, e to the power minus v, right? Here, yes, minus v will converges to this one. Let me put s here, e to the power s. Here you have d beta naught y, then minus e dx naught. Here x, no, this one. Dx naught y and this one. Okay? So you see if this y goes to the boundary and also this v, s goes to v, this one will converges to what? E to the power minus v, and this is exactly the Postman function, right? This is the Postman function. So if this y goes to Cassini, right? So this is the Postman function of, let me see, at x naught Cassini of beta x naught. So that's what we want, this Paschen-Sullivan measure. We have some progress, but not much. So next time, tomorrow, I will this measure, and also promised we will move on to the stochastic case and to see if we have other measures, interesting measures other than the Liouville measure and also the maximal entropy measure. So I stop here. Thanks.
Questions?
Liouville measure also depends on the base points you have chosen. What is the, I mean, what is the radon-Nicotian derivative if you change the base point to the Liouville measure? Is there a simple expression? Here it's written by the exponential of the Postman function. What is it then?
What is it?
No, you're taking the uniform measure
Yeah,
and then you're pushing it forward
yeah,
to get on the boundary factor, on the unit tangent matter factor.
yeah,
You take the product measure
yeah,
and push forward measure on the boundary.
yeah, yeah.
So if you change a base point, what do you get in the for this push forward measure? I
Okay.
think the question is, what is if you push forward? What is the relationship between the push forward measure? For orbit points, it seems it should be the same thing, but locally, I think there's a change.
Yeah. Yeah. You have some change, right?
Yeah,
You have change when you change your base point.
Yeah.
It's also another class of conformal class, right?